Okay. So when you throw things on a computer, you know you can use representation of the real numbers. You can use scientific notation and all that sort of stuff. But I'm going to show you a method of removing the dimensions from the problem because it also gives you physical insight into what the solution has to look like. So the way this works, I want to go back to my differential equation, which is that dv dt is equal to minus kappa v over m. And the way this is going to work, instead of using units like meters per second for v or second for t, I'm going to use some units that I'm going to make up myself. So I'm going to make up the following variable, capital V, which is going to be the number of times the initial velocity that my velocity currently is. So if I'm now at half the initial velocity, capital V, the variable, would be 1/2. So this is a dimensionless variable. And V0 is just the initial velocity. So that sets the scale for the velocities in my solution. And then capital V is just what fraction of that am I at. And for the time, I'm going to make up something similar, except I really don't have any good idea yet about what I should use. So I'm just going to make up the letter Greek T, or tau, as the unknown time constant, and this is the dimensionless variable. Dimensionless variable, and tau is just some constant. And later I'm going to pick a value for tau that simplifies my life. Okay? So for now, it's kind of an unknown. So in order to use this method, okay, I think I know directly how I can sub in over here. The question, though, is how do I get dv dt expressed in terms of my new variables? Whose rule do I need? Madame Chain? The chain rule? So dv dt will be d of big V, V0 with respect to that. But some of those things are constants, so I can just yank them out because they don't affect the derivative. V0 is just a constant, so it comes out. Can I yank the tau, which is a constant, out of the bottom too? By the chain rule. And I'm left with the dimensionless acceleration, d big V dt. Okay, now I substitute these two things into my differential equation, and I have V0 over tau is equal, d capital V dt is equal to minus kappa over m times V, which is V0, big V. Okay. So far it's been nothing but headache. Now I think there's some beginning payoff. So what do you notice? Yeah, the V0 now is gone. That can go away. All right. I'm going to throw the tau to the other side. And we have that dv in my dimensionless variables, dv dt, is equal to minus kappa tau over m times v. So now remember I told you we get to pick what value we'd like to use for tau. What value should I pick? Why don't I pick m over kappa? So then I have a really straightforward differential equation. I have dv dt is equal to v with a minus sign. I didn't want to factor the minus sign in because that is important for obtaining the exponential decay. So having done this, what is my initial value for capital V? 1. The velocity starts at v naught, and we're using v naught as our yardstick, and I have this time that comes out. That's the 1 over e time. By the time I separate variables here and integrate, I have the logarithm of v is equal to minus t. That is, v is equal to e to the minus t. When dimensionless time t becomes 1, the value of v is reduced to 1 over e of its initial value. What's 1 over e? About 37%. Okay? So in real-time tau, v drops by 1 over e, or about 37%. So before even doing the differential equation, just taking out the dimensions, I can extract from the constants in the problem what the characteristic time scale for the decay is. That's very handy. Yeah?
Why are we allowed to just arbitrarily set tau?
Well, as long as you're not changing it in the middle of the equation, it's a straight substitution. So if you believe in the rules for taking a derivative of a product, then you should be happy with it. That is to say, it's the moral equivalent of saying, well, I have this equation when I use meters per second, but would I have a different equation when I use feet per second? No, you just have to scale the values. Okay?